here you don't shoot a laser, it just, you know, because the energy that's around it, an electron goes to an excited state, and then the electron goes back to the original state, and that corresponds then to an energy level, and that corresponds to, or a certain energy difference, and that corresponds to a wavelength of emitted light. You know, you emit photons at a given wavelength. That's called chemiluminescence, and so different species have characteristic, you know, energy transitions, and with that they have characteristic wavelength at which they, you know, appear. And so many of these you can't see because they're outside the visible range, but some you can see, CH, OH, I think C radical, these are some that you can see, and you see some of these that appear more in the rich, for rich combustion, like I think CH is a little more in the greenish color, and OH is more to the bluish color. So that's what the colors are. Okay, so let's see what comes next here. Okay, so aim of this course is we want to develop an understanding from both physical and chemical perspectives. And of course, combustion is the interaction of the two, and you know, and not just one of these. So we start out here with some fundamentals. We'll talk about thermodynamics, fluid mechanics, heat and mass transfer. Actually, we would also talk about kinetics, but we're not talking about kinetics here because there's a special course on kinetics. I'll talk a little bit about kinetics, the things you need to know for my course. That's what I'll talk about, but not very much. And then, you know, there's some application. I talked about applications before. But really, I have to say, Professor Law at some point, he wanted me to call this applications, or he wanted me to focus more on applications also. And I said, if I focus too much on application, I can't tell you everything about the theory I want to tell you, so there's not much application. The course here is based really on a course that here Professor Peters from Aachen gave here 2010 at the summer school, and there's also a text, and the text you can download from our website. And maybe it's not exactly, you know, what I teach now, but, you know, roughly. And then we have two parts here. Fundamentals is laminar flames, and then turbulent combustion is the second part. And then at the end, we have, I'll show you this here, right? So fundamentals, turbulent combustion, we talk about here mass balance and combustion systems. We do this really fast because most of this, I mean, it really introduces nomenclature, and most of you know probably, and maybe it's just to pick everyone else up and move us all to the same page. So this might be a little boring going through all these things. I'll try to do this fast. So we have more stuff for the other topics. And then thermodynamics. Thermodynamics, of course, first law of thermodynamics, second law. The first law will tell us something about flame temperature. The second law will tell us about chemical equilibrium. So that's what we'll talk about. There are a lot of really, really interesting consequences of these discussions. And then there's a section here also on governing equations, which we'll not discuss. It's in your handouts. If you're, you know, struggling with the governing equations, you know, have a look at these. If you want to know how they're derived, is also shown there. But we're not going to talk about this. I assume that you know, species transport equation, that you know energy equation, and we use this usually in very simplified form here, anyways. So is not, and I assume that you know. If you look at a partial differential equation, if you look at a species transport equation, I assume that you know what the different terms are. If you don't, then maybe come to me, and in one of the breaks, I'll explain you what the terms mean. But you know, what's the convection term? What does it do physically? What's the diffusion term? That's important to understand. Anyways, and then we'll talk about flames. Now, there's a section missing. There should be a section on... Is this the fire alarm that I caused from... So... Sorry? This is a... I didn't get it. They don't send this to Germans. So, I mean, leave the Germans behind. You know, everyone run, but no, anything we need to worry about at this point? Yes or no? No. Okay, there's one section missing. What's missing is homogeneous reactor. Homogeneous reactor is something we would teach. I would tell you, I would show you a nice analytic solution to, for ignition delay times, to compute ignition delay time. But we're not going to do this because Professor Law told me, you know, 10 years ago when I did this first time, this homogeneous reactor is chemistry, okay? So the chemistry part, Professor Sarati is going to talk about this. So we are going to talk about premixed flames, flame structure, diffusion flames, and so on. And then also we're going to have one class here on FlameMaster as a code that we have developed over the years that we use to compute flames. It's like, you know, some of you might know Chemkin or Cantera. So it's a code like this. It's an open source code. At some point, the reviewer came and said, this is not open source. And I said, this code was open source when open source has not even been invented, okay? because I wrote this code as my master thesis in 1992, okay? And it was online, you know, you could download it at that time. The term open source wasn't even coined, okay? So FlameMaster is a true pioneer. So you can download it here, install it on your laptop if you have one, and then, you know, during the session, you know, you can walk along and do the calculations and stuff. You go to this thing and you have to ask for a password, and then somebody will send you a password. That's why the reviewer, by the way, said this is not open source, because, and it comes with a thing that says, if you are in a company, you have to get a license. And I think a lot of companies are using the code, but very few ask for a license. But anyways, okay, second part, we'll talk about turbulence. There will be a section just on turbulent flow, you know, incompressible turbulent flow. And then we'll talk about premixed combustion, talk very briefly, I think, about non-premixed combustion, and then we talk about modeling, different models that are being used. And then at the end here, there are two special topics. One is machine learning, because machine learning, I mean, everyone talks about machine learning, and I mean, there's really a lot of interesting stuff, and I'll just, you know, show some of the things that we're working on in machine learning, which are interesting, and I tell you a little bit about what the pitfalls are, what's difficult sometimes in using these or, you know, doing it right. And then hydrogen. Hydrogen is a topic that we have been working on since a long time. I mentioned earlier, hydrogen is very, very different from other fuels, and so we'll talk about hydrogen also, what's special, and you know, how can we explain it. Okay, so then we start here with a second lecture, or the first part really after this introduction, which is on mass balances and thermodynamics. Thermodynamics, of course, it doesn't tell you. Thermodynamics is, let's say, the opposite of kinetics, right? I mean, or it's not the opposite, but kinetics tells you how fast are we moving in a certain direction, but thermodynamics tells you what is the direction, okay? And where will you end up if you have walked for a long time? So that's what thermodynamics tells you. And in order to understand all of this, to talk about thermodynamics, we need to have a lot of definitions, concentration, thermodynamic variables, and so on. And we need to know how to do mass and energy balances for multi-component systems. So of course, multi-component is very important for combustion. Okay, so this is the section, and then you see here always the subsections in this section, and we start here with these definitions. And again, we'll go over many of these very quickly, and if it's too fast, then you know, let me know. And if it's too slow, let me know also. I can go faster. I can also talk twice as fast if you want me to talk faster. But anyway, so in combustion, very often we have many species, so we need to worry about many species, multi-component systems. First of all, we introduce the mole number, which is the number, you know, of moles in the system. Here we call this N, is just here how many times this number of moles do you have in the system. So it defines the Avogadro number. The Avogadro number is nothing else than a counting unit, okay? We don't always want to say 10 to the 23. It's like a dozen. You know, we say 5 dozen, and here we say 5 moles. It's just it's exactly the same thing otherwise. And then we introduce a mole fraction, which is the mole number for a given species divided by the total number of moles. So I have a container, and I have 2 different species, or let's say this room. I have oxygen and nitrogen in this room, and then I have so many moles of nitrogen, and I divide this by the total number of, or so many molecules, let's say, of nitrogen. I divide this by the total number of molecules in this room, and then that gives you the mole fraction. So these fractions, because they're non-dimensional, they're very important. Then we can also define mass, partial mass of a component, and in a similar way, we define mass fraction. It's the mass of component I divided by the total mass. And one thing that's funny in combustion is that we always do both. I mean, in fluid mechanics, people talk just about mass, you know. But here we talk about sometimes mass and sometimes moles. Why do we need to make it complicated? Why not just talk about one? Because mass, of course, very good, because mass is a conserved quantity, okay? Total mass is conserved, here these partial masses, they change, of course, because of chemical reactions, but total mass conserved. That's really good for balancing. So anytime we write equations, we want to use mass. At the same time, we are worried about chemistry. Chemistry involves reactions. They have a stoichiometric coefficient. Molecules, they react together, you know, in even or in integer numbers. And so that's why moles, counting molecules and atoms, is very interesting. That's when we use mole fraction or moles. And so, of course, there's a mean molecular weight, and there's a conversion between mole and mass, or mole fraction, mass fraction is trivial. It's relatively trivial. Now, another thing that's really interesting here, I mean, just to make it even more complicated, is the element mass and the element mass fraction. So I could also count in this room all all oxygen atoms, okay? So I have O2, so I count all the O2 and multiply it by a factor of 2. But then also there's humidity here, so we have I went running this morning, and I told Professor Law the humidity this morning was 120%. You know. So, anyways, here is okay. I have water here also, and each water carries 1 oxygen atom. You know, so I can add these all up. And element mass fractions are very good because elements also are conserved, right? I mean, we are not worried with nuclear reactions. For us, elements are always conserved, and quantities that are conserved are very, very powerful in the analysis. So that's why we define this element mass fraction shown here. So this is the mass of species I, okay? So this is the mass of species I. I divide it by the molecular weight of species I. That gives me the number of molecules of species I. I multiply it with this matrix. What is the matrix? Aij is number of atoms J in species I. Okay? So let's say in my example, O2 has now 2 O atoms. Okay? So I multiply with 2. Now I have the number of atoms of species I. And then I multiply it with molecular weight, gives you the mass. And of course, I sum it over all species, you know, H2O, O2, and so on. Okay, so this looks a little complicated, but, you know, I mean, now you understand it. Now we don't need to worry about it. We just need to put in the numbers. And we can also define an element mass fraction. So this was the element mass fraction. you know, for each element, you know, H, O, N, and so on. And then, of course, these mole fraction, mass fraction, element mass fraction, they're defined always to be 1 if I sum them up over all species. And then, to make it yet more complicated, there's another way of counting, you know, mass or matter, which is the so-called concentration. Or partial molar density is the same thing. Sometimes we write it like this: X would be a species. CH4 in these brackets means that's the concentration of CH4. But mostly we write it like this. Concentration of I is the number of moles per volume. Yeah. That's the only thing one needs to worry about. It's not non-dimensional, right? It's not like a mass fraction. Concentration is not a mole fraction. Very often, I mean, I think I'm not tied to terms, okay? But sometimes, if we don't use the right terminology, we confuse each other, okay? So here's one thing I want you to remember. Mole fraction is not concentration. Very often people have X, and they say, oh, the concentration is this or that. No, a mole fraction is non-dimensional, and concentration is not non-dimensional. It's mole per volume, okay? And then I can define the total molar density, or the total concentration, total number of moles per volume. Why do we use concentration? Because it usually appears in a reaction rate, okay? So that's why we use it. It is the density, so this is the mass density. So interesting. Concentration, the total concentration, is for moles the same thing as the density here for the mass. And of course, there's a conversion between mole fraction and, see, now I make the opposite mistake. Between concentration and mass fraction. You know, it's just given here. You can very easily derive it. It's just important because reaction rates are proportional to concentration. But we want to write the balance, the species balance in terms of mass, okay? So we need to be able to convert concentration into mass, that's all. Density times mass fraction divided by molecular weight. Ideal gas equation of state, everyone knows. What's interesting is I have a multi-component system, and I assume I have an ideal gas. Then the individual components, they don't know anything of each other. In this room, I have oxygen and nitrogen. The assumption of an ideal gas in this room is really, really good, okay? This means the oxygen doesn't know there's nitrogen. In fact, each oxygen molecule doesn't know there's another oxygen molecule, right? I mean, that's the assumption of an ideal gas. Pressure goes to 0. The molecules are so far away from each other, they don't know each other. It's like, you know, I live here, you know, one of you lives in Europe, and somebody else lives in Australia, and one in Africa, and we don't know each other. Okay, so that's ideal gas. You know, we're so far away apart from each other, which means I can take this room, freeze the molecules for a second, and then take all the oxygen molecules out, take them out of the room, and have only the nitrogen left. Okay, and the ideal gas equation of state applies to this nitrogen. Or I could have done the opposite and just take the nitrogen away, and then this applies to oxygen. And of course, then everyone knows, air is 21% by mole, oxygen, and 79% by mole nitrogen, right? Which means then if I have only, you know, 21 out of 100 molecules, also the pressure is only 21%, right? And so here is Dalton's law. So here this is shown here. So this is the room. These are just the oxygen, this is just the nitrogen, and they are like two independent systems, and the pressure of the two just adds up. I have a partial pressure of nitrogen, I have a partial pressure of oxygen, and the sum of them gives me the total pressure, okay? And this means, and that's the important part of the story, the partial pressure divided by the total pressure is the mole fraction. Okay, that's for an ideal gas. That's, you know, So that's very important. So in the lab, when you want to, you know, mix together a certain mixture in terms of mole fraction, you just do it by the partial pressures. You know, you first put 21% bar oxygen in the tank, and then 79 bar of nitrogen, and then you have mole fraction composition like the air. Okay, each of these molecules, of course, takes the entire volume. There's an example here, you know, how to compute mass fraction, mole fraction, how to convert them into each other, element mass fraction. If you can't sleep tonight, that's what you can do. Okay, then let's talk about chemistry for a second. Here I just want to introduce two, you know, what's the difference between an elementary reaction and a global reaction. Elementary reactions are reactions that really happen like this on the molecular scale. So when it says H plus O2 goes to OH plus O, it means there's an H radical flying around, there's an O2 molecule, they bump into each other, and they do something and they fly away as OH and O. That happens, I mean, you can look at it, it happens like this. Global reactions are not like this, they just give you a conversion ratio. If I have chemical reaction, I put H2 and O2 in a tank and I light it up, and it gives me, then for full conversion, it would give me, you know, these two H2O. And there are many reactions that happen in between, but this reaction will not happen like this on the molecular scale. You will not have two hydrogen bumping into one oxygen and, you know, magically water comes out. So that's the big difference. And then if we look at, by the way, I mean, these are two examples here. Why do I use these two examples? Why do I use this reaction as an example? Usually, in my class, I ask questions only because then I can have a sip of coffee. And if you want to trick me, you have to answer so quickly that I can't have a sip of coffee. No, go ahead. Go ahead. I mean, first of all, I mean, so the answer is because hydrogen, you know, is in many fuels, in hydrogen and also in hydrocarbon fuels. So this is a reaction that happens for most fuels. That was the answer. That's true, but there's a more powerful reason. I mean, that's part. Let's say that's 30% of the answer.
The top reaction generates two.
Yeah, the top reaction generates two radicals. That's let's say now we're at 70% of the answer, and I'll give you the remaining 30%. This is the most important reaction in combustion, period. Okay? So you might as well now take 5 seconds and memorize this reaction. This is the most important reaction in combustion, okay? If you understand this reaction, you're 50% there. You know, maybe not quite, but anyways, because of the reasons that were just mentioned, we'll see this later on. This is a really, really important reaction. No combustion without this reaction. Oh, here it's again. Okay, so elementary reactions, they observe, of course, conservation of elements, and global reactions also do this. They, you know, tell you about a real collision. You know, we denote this here by an arrow. They usually go the other way. Also, they go forward and reverse always, and so sometimes we write this double arrow. We use here in this course sometimes. We use this little circle here to say it's a radical. You know, I mean, this is not commonly done, so don't think, you know, you always have to do this. It's just here to make it easier for our students to see what's a radical and what not. Because later on we'll say radical is really important to make that distinction. Then global reactions also observe, of course, element conservation. They do not take place on the atomistic scale, and we use an equal sign here. Now, this reaction just means 2 mole hydrogen react with 1 mole oxygen, give you 2 mole of H2O. And then, of course, for global reactions, you can also take half or twice, you know? So you could say, okay, instead of saying 2H2 plus O2, I can also say H2 plus 1/2 O2. It's exactly the same thing, because there's no reaction rate or so assigned to this. And of course, for elementary reactions, you cannot do this. There is nothing like, I mean, O is not 1/2 O2, right? I mean, it's not the same thing. So you can also write this in terms of mass by multiplying this here by the molecular weight, and you get a reaction, you know, that's based on mass. But of course, it's much easier to do it this way. Now, this also, again, about nomenclature. When we write this in more general terms, we use the Greek letter nu for the stoichiometric coefficient in the reaction. And we say nu prime, then we mean it's the reactant, and we say nu prime prime, it's the product. So nu prime is all the left-hand side species, and prime prime is the right-hand side species. We can do this for both elementary and global reactions. And these nu prime and nu prime prime, they're defined to be positive. Okay, so here the stoichiometric here nu prime for CH4 is 1, and nu prime for H2O is 2. Okay, they're defined to be positive. We can also you know, involve the sign here. We define a new quantity nu without the prime or prime prime, and that actually carries a sign. So it's nu prime prime minus nu prime, so it's negative for the reactants, positive for the products. So here, same thing. Nu CH4 is -1, and for H2O it's 2, which means now if I write a reaction equation like this, so this here is the concentration, the change of the concentration in time is equal to the reaction rate, the times how often does this reaction proceed, times the stoichiometric coefficient. And you see then here for methane, it's negative because it's consumed, and for water, it would be positive because it's produced, okay? So that nu carries the, so sometimes we go back and forth between, and then we need to worry about the sign. Okay, how to formulate a global reaction. You know, this is done here for a general hydrocarbon, and you know how to do this. I'm not going to explain this. Okay, but the next thing now also relates to global reactions. Or, I mean, maybe it could also be done for a elementary reaction. But now this is really, really important, okay? So, I mean, if you're really tired, just get up and sit down. You can always do this if you get really tired because you didn't follow my advice and had no food. Who had food today? Okay, breakfast you can have, but no lunch, okay? So, at least stay easy, go with a salad or fruit. Anyways, you know, I mean, just do this. Coupling function is really, really important. It's very simple. It's a trivial concept, but it's very, very important and very powerful. Okay, here's the question. We have a global reaction. 4H2 plus 2O2 goes to 4H2O. Question is, what's the question? How many, so consider conversion of 8 molecules of hydrogen. How many moles, how many molecules should this be, of O2 have been converted? Sorry? 4, exactly. So 4 of these. Okay, so it's very easy. And how often has the reaction taken place? You want to convert 4. See, the difficult question, nobody answers because they're too difficult. The simple question, nobody dares to say anything. But this is really a simple question. I mean, oh, now the pressure is even higher. No, it's a difficult question, okay? How often has the reaction taken place if 8 molecules of hydrogen have been converted? 2, twice, okay? So it's very easy. I mean, you can just take the number of molecules divided by 4 twice, okay? We said 4 oxygen divided by the stoichiometric coefficient twice, okay? Write this in equations. So this is a general global reaction, and then here the concentration rate of change, dC by dt for a species, for species I, is the reaction rate. How often does the reaction take place per unit time and volume, times the stoichiometric coefficient. And remember, note is negative on left-hand side. But this is the the species equation. And now what we do is so this here is mole per volume. So I multiply the whole equation by volume. Okay. So I have then Ni here on the left-hand side, the volume on the right-hand side, and I divide the whole equation by the stoichiometric coefficient, which is a constant, so I can just take it in the differential. It doesn't appear on the right-hand side anymore. And you see, now just look at the right-hand side. The right-hand side is independent of the species I consider, okay? It's independent. The right-hand side is the same. If I write this, it is an I, can write this for H2, O2, or for H2O. The right-hand side is always the same, okay? And you see that means, of course, it's an equal sign. If an equal sign, the left-hand side must be the same, okay? It must be equal. So also the left-hand side does not depend on the species. So Ni divided by nu I is independent of the species, okay? That's the important point. Change of mole number divided by stoichiometric coefficient, that's what we have done earlier here. dNi divided by nu I is the same for all species. Okay, that leads us to the coupling function. So this is the same for all species. So I can say, I can take one reference species here, 1, I call it species 1. Maybe it's the fuel. Let's call it the fuel. And then, this is the same for all other species. I divide this here by the molecular weight. Sometimes we write the molecular weight by M. We denote it by M, sometimes W. It's not good, but it's just what's in the slides. And, at some point we should change this. But also we want to challenge you. So this is molecular weight. And then, so I can write this for mass. I divide the whole thing by the total mass. So I can also write it by the mass fraction. And here comes the interesting thing. Now take I to be oxygen and the reference species fuel. Then I can integrate this over a reaction. Take a container, it has fuel and oxygen, and then, so it's an initial state. Here this is, U is unburned, and then I let it react up to a certain point, and so I integrate it up to that certain point, and I get, here's nu and M in the denominator, and I get YO2 minus YO2 unburned, Y fuel minus Y fuel unburned. And so, and by the way, sometimes for the fuel we use F, sometimes we use B. Why do we use B for the fuel? Yeah, I was just on my way to get some coffee. Brennstoff is German. It's German for fuel. Okay, so anyways, you learn some German here on the way. Okay, so that's what we call a coupling function. You can write this for any other species also. You can, integrate water, and then if you do it for water, you see that that the nu now has a different sign. So when one is consumed, the other one is formed, and you get different here. These coefficients are different. But you can. So what it means really is, if you assume a one-step global reaction, only one species is independent. Okay, all the others, they can be expressed by the first one. So why did I say earlier it's very powerful? Because take CH4 plus 2O2 gives water and CO2. You have 4 species, but only one is independent. You don't need to solve 4 equations. You can solve only one. Now, if you solve 4 or 1 on a computer, it doesn't really make a difference. But when you do analysis, you have 4 coupled differential equations. You are not going to solve the system. But if you have only one, that makes it much simpler. So that's what we always do. Always use coupling functions to do this. And by the way, there's also a coupling function with a temperature. So temperature can always also be expressed as function of, some species or vice versa. Okay, good. Coupling function. Here's an example question. A closed system contains hydrogen and oxygen. Through combustion reactions, 1 kilogram of hydrogen is consumed. what mass O2 has been converted, how much air is needed. And so I, just take exactly this thing, take this here nu O2, MO2, bring it to the other side, and then you get this ratio here, and we call this nu, this ratio. And you will see this ratio that comes back later on. We call it the stoichiometric mass ratio. But anyways, so, this here is 1 kilogram, or, multiplied with total mass, this is 1 kilogram. Nu here is stoichiometric coefficient from the equation, and here's the equation, is 0.5 times 32, and then stoichiometric coefficient is 1 times 2 gram per mole, so it's 8. And then, so 1 kilogram of hydrogen, you need 8 kilogram of oxygen. And then, times 5 roughly gives 26 kilogram of oxygen, of air. Isn't that interesting? You want to burn 1 kilogram of hydrogen, you need 26 kilogram of air. Which means, as that's what I said in the beginning, in the mixture, the fuel mass sometimes is really not important. I mean, for hydrogen especially, it's not important. Here's another one, interesting question. How much CO2 is formed when burning 1 liter of gasoline? I should have asked the question before showing it here. But, so, assumption is, density of liquid gasoline is roughly 0.75 kilogram per liter. Gasoline can be approximated by isooctane. Of course, isooctane is used in the definition of the octane number. And so it has similar properties to gasoline, and it's just an assumption here. One-step global reaction for isooctane plus 12.5 O2 gives CO2 and H2O. And then again we write the coupling function, this time between fuel and CO2. And now you see here we get a minus because of the, that's why you have the minus here then, because, no, here we have the minus, sorry, here the plus. And then you integrate this, and you can plug all this in. 1 liter of gasoline gives you 2.3 kilogram of CO2. That's a lot. I mean, you drive your car, if you have one, and you don't need to go very far to burn 1 liter of gasoline, and that's already 2 kilogram. And I mean, yeah, I think it's a lot. I mean, and in terms of space, it's 1 cubic meter. Because you look at your car, you don't see the CO2 coming out, right? I mean, it's just, I don't know, it's just there, but you don't see it. Anyways, stoichiometry. For stoichiometry, again, we first need to write here the global reaction, and again, we don't need to do this, but stoichiometric, what does it mean? Stoichiometric. Stoichiometric means, the amount of fuel, the amount of air, they're exactly in the ratio that, or in proportions that they follow the global reaction, and which means, if one of them is fully consumed, the other one is also fully consumed, right? That's what stoichiometric means. And then when we have too much oxidizer, we call it lean. If you have too much fuel, we call it rich. And then here when we talk about one-step global reaction, we say in lean combustion, you have a lot of oxygen and you have not enough fuel, and then you burn both, and at some point fuel is gone, and then the oxygen is left over, right? Vice versa, in rich combustion, the oxygen is consumed, and then the fuel stays over. The reason why I say this now is, so that's what we assume. That's not really what happens. What really happens, we'll see this later when we talk about flames, is that, so for hydrocarbons is not, for lean combustion is exactly what I said. For rich combustion is not the fuel that stays over. The fuel is typically converted first to CO and H2, and then the CO and the H2, they remain left over. Anyways, that's what this means. And so stoichiometric, we can just get it from the global reaction. So what's the stoichiometric mole ratio between O2 and fuel? It is exactly the ratio of the stoichiometric coefficients in the global reaction, right? I mean, it's just nu O2 divided by nu fuel. And, okay, if I write this in terms of mass, you know, I get this ratio and then also the molecular weights, and I get this. And this is exactly, you know, this new factor we defined earlier in the coupling function. So that's what we call the stoichiometric mass ratio. Nu just tells you how much oxygen do I need to burn, how much kilogram or mass oxygen do I need to burn 1 kilogram of fuel. And typical values we just saw for hydrogen, it was 8. For methane, it's 4. For dodecane, it's 3.5. So typical hydrocarbon fuels is around 4. And for hydrogen, of course, different. But 4 also means that I have 4 times more oxygen than fuel. And 4 times more means 4 times, you know, the factor of 5 again means, I mean, a lot more air than fuel. Okay, so, right. Okay, so, I mean, this just to show again, this is exactly the same thing that we had here in the coupling function. Yeah, there's no surprise. There are a few other quantities. So, by the way, always when you see the green thing here with header with the asterisks, it means we're not going to discuss this here, is you know, added topics that you can look at if you really can't get enough of all of this. It's like the, what do you call this for the movies? The takeouts or whatever. They have it on the DVD. There are no DVDs. You guys still know what DVDs are? Just joking, but they used to have the cutout scenes, you know, that's what this is, a cutout scene. So there are a few other quantities we can define, but we'll go over this quickly. And then, of course, I mean, important is the equivalence ratio. Why? Because I can tell you, what is, I mean, let's say I do an experiment, I have a box, I put fuel and air inside, and I can tell you what's the mass ratio of oxygen and fuel. And let's say I would tell you the mass ratio, oxygen fuel is like 9, okay? And, you know, for methane. And what does that tell you? I mean, it's difficult, you know, to know what it means. So, but there's a stoichiometric mass ratio, you know, which was this nu. And so what we do now is just we take the mass ratio and divide it by the stoichiometric mass ratio. Okay? I mean, the mass ratio was we take the ratio of both. This was actually had the oxygen in the numerator. So here's the inverse, but the equivalence ratio is just the ratio of fuel to air divided by the stoichiometric ratio of fuel to air, okay? So that means if it's 2, if it's 1, it's exactly stoichiometric. If it's 2, it's you know, you have twice as much fuel as you need. 0.5, you have half as much fuel as you need. So it's very easy to understand. Interestingly, in Germany, so I don't think I use this here, but most combustion people talk about the air-fuel ratio. It's just the inverse, nothing else. Right? So there's a lot of confusion there also because equivalence ratio, air-fuel ratio, and they call it lambda. You know, lambda is the air-fuel ratio. But we're not going to discuss this here, just if you're on vacation in Germany, you want to do a little bit of combustion science. Don't get confused, you know, when people use lambda. Now, what's interesting about this also, I can divide this now here by the molecular weight of fuel in the numerator and denominator and oxygen. And then you see I can write the exact same thing in terms of moles, the whole thing in terms of moles, either or mass fractions is the same thing, okay? Unfortunately, what we usually do, and it's not written here, what we usually do is we do a mix of both. We usually use the numerator, the actual composition in terms of mass, and the stoichiometric composition in terms of moles. Why? Because the stoichiometric composition, you just get it from the global reaction, okay? And you know, very often we use mass fractions in balances. And so if I do that, then of course you have a bunch of molecular weights here also in this equation. So you can either use it as all mass fraction, all most fraction, or, you know, the mix, but then you have to be careful. Okay, and then mixture fraction. We define a quantity that we call the mixture fraction, which is something like an equivalence ratio. Basically, it gives you the exact same information as the equivalence ratio, and we use this very often in, you know, we talk about non-premixed flames, and I'll tell you later on why we don't just use the equivalence ratio. So in a non-premixed flame, I showed you earlier, we have two separate streams. We have the fuel stream. I mean, here in the cigarette lighter in my experiment, it comes from the bottle. And then the second one is the air, which is just the environment, but it could also come from a different nozzle if you have a closed system. So these two, they mix and burn. And so the mixture fraction just tells you locally how much of the mass that you have originates from the fuel stream and how much of the mass originates from the oxidizer stream. So this means, for example, if you have H2O, okay, then if I have pure H2O, I know, so H2O has a mass of 18, right, 18. So I know 2/18, 1/9 came from the fuel streams, the hydrogen, and 1/9, 8/9 came from the oxidizer stream, okay? So it doesn't matter if it has burned or unburned, we just look at the elements, where did they come from which stream? Did they come from the fuel stream or from the oxidizer stream? Okay, so this is how we define it then. We just say the mixture fraction is, so we say fuel stream is subscript 1, oxidizer stream subscript 2. So mixture fraction is the mass that originated in the fuel stream divided by the total mass. So mixture fraction equal 1 means it's pure fuel, mixture fraction equal 0 means it's pure oxidizer, you know, and in between it gives you the mass ratio of what came from where. And so we can derive an equation like this here by saying, again, so this is the mass fraction of fuel in the fuel stream. 1 means it's the fuel stream. 2 means the oxidizer stream. So this here is typically equal to 1, but it, you know, doesn't have to be. And this here is typically, I mean, 23%, you know, is air. So, but, you know, could also be diluted or with EGR or whatever. And then we look first at what happens before combustion. So this is the definition of mass fraction. Here is mass fraction is the mass of fuel divided by the total mass in the stream. So if I take this and divide it by the total mass, then on the left-hand side, I get the mass fraction. On the right-hand side here, M1 divided by the total mass is the mixture fraction. So this is the relation between the fuel in the unburned and the mixture fraction. And I can do if I do the same thing here for oxygen, this is what I get, okay? And then this was the coupling function we had earlier. And now, so this is fuel mass fraction, oxygen mass fraction, and this is the same in the unburned, before it burned. And now I just plug these in here, I mean this here, and then I get introduced this Z. I can solve this for mixture fraction, and this is what I get, okay? So that is the definition of mixture fraction, and you see here it has the mass fractions of you know, fuel in the fuel stream, oxygen in the oxygen stream. So these are constants that are given by, you know, the boundary conditions, how I define this, and then you see again here this stoichiometric mass ratio appearing, and the local concentrations. And what's interesting about this, because it really just counts elements, I mean, it looks at where did the elements come from. It doesn't matter if it's burnt or, you know, if it burned or unburned. So if I have a system with a fuel-air mixture, and I evaluate, given this, the mixture fraction, you know, get a certain value, and now I burn it, and the mixture fraction doesn't change, okay? Because I mean, it just looks at where did the elements come from. Okay, even though I have YB and YO2, but if I burn a little bit of O2, I have to use nu times YB to burn the same thing. So that's why these two cancel each other out. Anyways, because of this, for stoichiometric mixture, the first two are the same. Nu times YB and YO2 are the same. And so they go away. And so the stoichiometric value of the mixture fraction is this with just these two, removed, is this part, okay? And I can write it in a different form. And the typical value of stoichiometric mixture fraction, that's again, is the mass between fuel and air at stoichiometric conditions. And that's for methane, the value is 0.05 or 0.055. But let's say 0.05, which means you need 20 times the mass of air than the mass of fuel, okay? So these are typical values. If you take a heavier fuel, like N-heptane is 0.062, it's roughly the same, okay? And for hydrogen, it would be even less. So very typical values are around 0.05. But if you have dilution, maybe of the fuel stream and so on, then this can also change. Okay, so there are many different definitions of mixture fraction. They all mean the same. The one I showed you now was basically is based on a one-step global reaction. You can also base this on elements, and that's here this bigger definition. You can look this up. You get something that looks a little more complicated, but it's that's based on elements. But and there are other definitions, like I introduced a definition a long time ago, where I said, I mean, the nice thing about mixture fraction is, I mentioned this earlier, it doesn't depend on the combustion process. In the unburned and the burned, I mean, it's the same value. It's not changed by combustion, the value, okay? It's only changed by mixing. And which means if you write a transport equation for mixture fraction, it has no chemical source term, okay? Because it doesn't depend on the chemistry. So at some point I said, let's define it just as the solution of the transport equation, okay? That's another one. And with appropriate boundary conditions. But so there are many different definitions. What's interesting, I said in the beginning, there's nothing else than the equivalence ratio. And you can actually show this, and maybe we don't need to go through these, I mean, it's just basically using the same relations and the coupling function and the definition here of the stoichiometric value, but then you can derive an expression like this. The equivalence ratio is, this in terms of mixture fraction. So if for a certain fuel, it depends on the stoichiometric value also, which depends on the fuel, but if you fix the fuel, then, and I give you a value of, let's say, of the equivalence ratio, local value of equivalence ratio, then you can also, you can immediately determine the value of mixture fraction or vice versa, okay? So this just shows it's exactly the same as equivalence ratio. So the question then is, I said we use this for non-premixed flames. Why do we need to introduce yet another quantity? Yeah, they burn at stoichiometric, and so, but you could also say stoichiometric. I mean, if you look at this, stoichiometric means here, I mean, if I say Z is equal to Z stoichiometric, then all of this is 1. And so, I could also say they burn at an equivalence ratio of 1, okay? That's true, but it doesn't really justify why do I need a new quantity. Yeah, you said, if I understood this right, it allows you to also consider cases where you have very high equivalence ratio. And yeah, I'm not sure if that really is the point I wanted to make. Yeah, I mean, the nice thing is, you see, if I have an equation, I mean, here, if I have an equation for fuel mass fraction and I have an equation for oxygen mass fraction, it's just a linear combination of the two, right? I mean, I can easily derive an equation, a conservation equation for this. But really, let's say I can do the same thing also. I mean, I have an equation here for this, for Y fuel and for YO2. I could also derive an equation for equivalence ratio. But what's the problem with that equation? And that's really the point. Yeah, exactly. So the point is, in a diffusion flame, you have pure fuel somewhere where the equivalence ratio is infinity. Okay, that's an equation that's very difficult to solve, and that's why we use mixture fraction. Mixture fraction goes from 0 to 1, yeah, very well defined, and no infinity or whatever. So you could look at mixture fraction just as a, rescaled equivalence ratio. That's exactly what it is. It tells you locally in the flame, it would tell you here's equivalence ratio, the mixed fraction is 1, super rich. Here's 0, so super lean, and somewhere in between is stoichiometric, and here's the problem, or I mean, it was a little advantage of the equivalence ratio is, it's 1 when it's stoichiometric. I mean, that's beautiful. But mixture fraction is 0.055, whatever. But we know this for a given fuel, we know this value, and that helps us then also. Okay. Yeah, I mean, you can also define this for multi-component fuels. You can also define it. I mean, that's the point. Sometimes the question is, what if I have some fuel also in the oxidizer stream? What do I do? Does the fuel come from this side then or from that side? And the point is just, think of the original definition, is it's just the mass from one stream and the mass from the other stream, okay? So, define, I mean, it doesn't matter how the streams look like. You have one stream, so if I have a mixture fraction of 0.3, it means 30% from the mass come from this stream and 70% come from the other stream. That's it. How these streams look like, it doesn't matter, You call this the fuel or that the fuel, or it's a blend of fuel and oxygen, doesn't matter. Okay, so maybe we'll stop. I think there's a break now, and maybe we'll stop here and do this then after the break. But we start 8 seconds before, 4:30.